Good day, everyone. Um, so this is basically a tutorial, right, based on control system. We are going to be considering um, variety of topics. The first topic I'm starting with is actually the state space representation. And so this tutorial is basically um, based on problem solving problems. And I'm going to be assuming that we have some foundational concepts in control systems. So we dive into the state space representation. I have a problem here, which is a simple RLC circuit. And the goal is for us to develop a state space representation. So the state space representation just consists of some inputs and variables and outputs, the relationship between these terms. And these terms help in characterizing the system. So with this representation, we can be able to understand the response. We can able to get the response of that particular system at any particular time. And we could also be able to assess the behavior of the internal state of the system as we apply and input. So that's what the state space is. And so it could be in a differential form, differential equation form, could also be in a difference equation form. So, but this is the differential equation form. As we have an area of C circuit that I've drawn here. And like as I've said, the goal is for us to get the mathematical model in terms of state space. And so finally, if we are done with this, it should look in this form. This is a linear form because you can see that the order of the first derivative and the variables there are just unity. And so it's just a linear form. And so the first thing you s- you have to do when you see an RLC circuit is you recognize the storage elements there, and those storage elements will have variables attached to them. So, for example, in this circuit, we have a resistor, we have a capacitor, we have an inductor. And of course, we know that the capacitor and the inductor are the storage elements. And because we know that the voltage across an inductor has um, the current, the derivative of the current present. And so it is natural for us to choose the current flowing in that inductor to be a state space variable. And you see that also for the capacitor, same applies. It's natural for us to choose state space variable to represent the voltage flowing in the capacitor. All right. So if X1 is actually the current flowing in this inductor, then we know that the voltage across this particular resistor will be 0.5 times the current, X1. It's natural. If X1 is the current flowing in this inductor, then we know that the voltage in this inductor has to be 2 times X1 dot. It's natural. We know that. If the voltage, if the current, sorry, flowing in this inductor is X2, then we know the voltage flowing in this inductor has to be 3X2 dot. So it applies to all the elements here. And this particular problem, it has been stated that the output is actually the voltage across the two ohm resistor. So the goal is for us to get the state space representation. So after labeling these elements, these inscriptions, what we go ahead to do is we try to see how we can use some tools like the KVL and KCL to see if we can extract some useful information from the circuits. So we recognize that there are two loops in this system, loop one and loop two. Um, so with recognizing that, we can take the KVL across loop one, and that means that when we sum the algebraic terms, which are the voltages when we sum the algebraic sum of all those voltages, across each of those elements equals zero. So, for example, we have positive u of t minus the voltage here minus the voltage here minus the voltage in this capacitor equals zero. And if you rearrange that, you have the equation for x1 dot as the first state subsystem. Similarly, if you take KVL across loop 2, here you have minus x3, which is the voltage across this capacitor, minus 3x2 dot minus 2x2 equals 0. And by the time you rearrange the equation, you have the subsystem. Similarly, at node A, this time we pick a node A because we've run out of loops. So when you look at node A, you see that the sum of currents, all right, coming in and entering that loop equals 0. So that means that we can say that x1 is equals to this current here plus this current here. And so that's what we did here. And by the time you rearrange x3 dots, you have a subsystem there. And we know that the output is simply 2x2. It was stated in the problem. The problem has made us to understand that the output is simply the voltage across this 2 ohm resistor. And since we know that x2 flows within this path, so the voltage has to just be 2 times x2. So that's actually is the expression for the output. And so what we do next is we simply arrange these terms in a way that we could actually draw out the matrix. And so that is why for the terms for the expressions that x2 is missing or any variable is missing, we just multiply that by 0 or 0 just to capture all the state space variable, even if there are some that actually 0. So for example, x2 is not present in this first subsystem, so we just say 0 times x2. For example, x1 is not present in this subsystem, we just say 0 times x1. And that is how we arrange this equation. And from there, we form the matrix. So same thing for the output. If you observe, if you multiply um, these matrices, you get this output equation. If you multiply these matrices, you get this output equation. So how do you form the matrices? It's very easy. You just take only the coefficients of these state space variables and you make it in this form. So observe that this form is actually represented in the state space, the general state space form for a nonlinear dynamic system. So congratulations, you now know how to represent an RLC circuit into state space form. Watch out for the next example.